My name is Michael Gussert. I'm an engineer, research scientist. I wear many hats working at NVIDIA. My specific interests are in deep learning and transfer learning. And so I play a lot with simulated robots and Pytorch and all that stuff. And I've been going around on the forums, and I'm seeing a lot of interest in people using Pytorch in Omnigraph, which I have an interest in as well. So I thought I might take this opportunity to go through a method that I've found for loading a Pytorch model within an Omnigraph node and then activating it based on inputs passed into the model, and then passing those outputs then out of the node to other nodes. So let me just swap over the stream. And I haven't ever done a whole lot of live coding before, so we're going to be kind of learning this together. But so to get started, we're going to open up our Omniverse launcher, and then we're going to go to our library where we should already have IsaacSim installed. If you don't have IsaacSim installed, you can go to the Exchange tab and then search for IsaacSim. And then you can install it from here. So we're going to launch that, and then we're going to wait for RTX to load, which is always fun. So you can guys see what's going on. It's interesting. I mean, like, there are people here to chat with. I suppose I can just chat with them. Hi, I guess. While we're waiting for this to run. What if we have in chat? What are you interested in getting out of this stream? What are you looking to find out? You came here for a reason. Why are you here? What kind of hardware am I running? I'm currently running a 4090 internal board. So we have this system for requesting new hardware if we need it. And so you can get like boards that were used for engineering projects and are now available and receive that as a GPU. So I have a 4090 in my workstation, and it's extremely nice. I'm not gonna lie. IsaacSim beginner. Yeah, no, I get that feeling for sure. Story of my life. I feel like I'm always a beginner with this stuff. Yeah. It's the thing that we have to keep in mind, and something that we're going to have to keep in mind while we're going over this today, is that IsaacSim is very much on the bleeding edge. And when you're working with the bleeding edge, you have to be comfortable with sometimes getting cut. And in this case, there's a specific bug that prevents us from utilizing some of the features that we have in IsaacSim for capturing images from our camera sensors. And so I'm going to be showing you a workaround for that bug, and specifically how I and my colleague Renato, who actually is the real brains behind knowing where to search what and how we figured out how to get this working. So you have, let's say you open up IsaacSim, you have an empty stage, and you have a scene that you want to load. So let's load a. So this is a simple test scene that I use for some of my research. So we have a JetBot here in the middle, and the idea is that we're going to have this guy. We want him to drive around, and we want to record images. We want to take images from the camera within the JetBot, and we want to pipe that into a Pytorch model of some kind. And a really great example of this might be, let's say you want to do reinforcement learning, right? Let's say you want to train your JetBot to go and do something. The problem, the hard part about working with the raw image data is that it's a lot of information, right? And you would have to go through a full like convolutional layering system to process that visual pipeline into your feature vectors that you would then use for predicting what to do next. Alternatively, you could train something called a variational autoencoder, which takes the image from your camera and then encodes it down to a latent space. So it's an n-dimensional statistical space from which you sample a vector that represents the input of your image. And then you have a second model that undoes that and returns the image itself. And then you train those to make them identical. And what you get in the end is that this latent space encodes well that data from the image. And so a really useful example for something like this might be if you have a trained variational autoencoder, you want to reduce the amount of data from your input to your RL policy. And so you're going to use this autoencoder to reduce the size of the state and therefore make it easier to train. So a great first step for this is going to be to open up a new graph. So to do that, I went to Window, I went to Visual Scripting, and then I went to Action Graph. And this opens up a new graph. And then I'm going to open up a new empty graph. And what I want is I want on every tick, so when I hit playback here, when I run the simulation, and I have my controller controlling the robot, which I don't have right now to show. But if I did, I would run the simulation, and we'd want every single time this playback tick occurs, which means that the simulation is stepping forward through time and physics is happening and playback is occurring. We want to take the image from the camera, we want to pass it to this model, and we want to get the result. So to indicate that first event, we need something, actually that first thing is called an event. We need something called onPlaybackTick. So this is an event node in Action Graph. So this event node is going to just sit around in the graph and do nothing until we hit play, and then every single tick that goes by, this thing's gonna go, hey, I'm ticking, do the thing. And we connect this tick line to some other node to do the thing whenever this ticks. And so to load our model, the workaround that I found is to use something called a script node, which is a really excellent, I'm officially in love with this aspect of Omnigraph. The script node allows you to specify simple scripts that will be executed on this input execution. So over here on the properties menu, there's a script pane where you can do your editing if you want to. And there are some default code snippets that you can load, like the Fibonacci number. So I can take my tick, I can attach it to here. And in the script node, we have setup, compute, and then there's usually a teardown, but we don't need that here because it's real simple. But I can just print, let's say state.num1. And now if I look at the console, we can clear the console with this little button here on the left. And then we can hit play. And we can see it's counting up the Fibonacci sequence, right? And we just changed the script live, and now we're getting that occurring every tick. Okay, so there's some questions here. I need to slow down. This is a problem that I have constantly in my life. We have, when you speak about the camera, is it a sensor camera on the robot or the viewport camera? It's both. So for this specific workaround, what we're doing is we're going to set the camera on the JetBot to the viewport, right? So, and then we're going to rip the rendered texture from the viewport and use that as our input instead of using an actual sensor. And there's all this typecasting that you have to do that. So I'm going to show you how to do that. But so up here, there's this little camera button. You can use this to change to whatever cameras you have on the scene. The default is perspective. These cameras, perspective, top, right, and front, are in a hidden layer. So there are all these different layers that make up the scene in USD. There's a hidden layer called the render layer that we use to keep all the stuff like these widgets and where these cameras go and all that. So we are going to change the camera to the JetBot camera. And so now the viewport is set to this camera. And so we're going to pull this specific render from this object in Python using a script node. So I hope that clears up some. Should a camera sensor be on the bot? Yes, there is a camera sensor on the bot. We also have LiDAR and depth sensors. Yes, we do. Ticks equivalent to frames per second. What is the frequency of ticks? That's a good question. So yeah, so you should assume that a playback tick, that's a difficult question to answer. There are a lot of different ticks, right? There's a tick that occurs for whenever something happens in the user interface. So if you change something in here, there's a callback that occurs, and that callback is checked on a tick related to the UI. There's a tick that occurs in the rendering that determines when an actual image is created and then put on, and then sent out to be rendered onto the screen. There's another tick that that works for physics that actually does. Can we import custom Python modules in the script node? Yes, we can. We're going to get to that. Moving on, going back to our action graph. So now we want to modify this script node, right? We don't want to do all of our editing in here because that would be a huge pain. So luckily, we can specify a specific path. So in this case, I've pre-prepared a directory called live coding, which of course, now that I'm looking for it, I can't find, there it is. And then I'm going to specify this directory for the script directory, and we're going to make a new file in here right away. So let's just open up Visual Studio Code. So all this is Visual Studio Code, and I've opened this directory that pre-contains this model file and the actual weights for the model. And I'm just going to create a new file, and we're going to call this Pytorch node.py, and it's empty. And we're going to point our script directory to our Pytorch node. Now you want to be careful here. There is another minor bug. If you select this and you double click, this path is not accurate, right? It put it in d/Pytorch node, which isn't where it is. So if you want to make sure that you get this working, you have to go to, you have to select your code and then hit OK, and then that will get the actual path in this text entry line. So now we're going to load us just another, do a little quickie dumb one cleanup. There we go, cool. So I'm going to just copy all this. So I click and I hit Control A to select all, and then I hit Control C to copy. And then we go back into our code, and we're just going to paste this in as an empty template, right? Our node, our script node, has 3 parts to it. We have our setup, we have our compute, and we have our cleanup. Setup should only be called when the node, you think when you put this in that setup is called once when the node is initialized, but it's not. It's the first thing that gets called when you enter the node. So if you have specific setup that you want to do, you want to put setup in setup and then wrap this in an if statement to make sure that it only executes the once. Compute is what's the actual, if you look at the actual OGN Omnigraph nodes that we have defined, the compute function is that same compute function that's in that definition. So this is like the meat and potatoes part of the node that's getting processed. And then cleanup is what gets called when the node is destroyed or has to be removed. Now, so what we want to do is we want to be able to load a specific Python model in this Pytorch node. So we're going to start with some imports. So first thing we need is torch. And from torch, we need tensor. And we're definitely going to need numpy. You can't ever not have numpy. Numpy is just need for everything. And And then we can also put, yeah, this is a good start. And now we want to be able to define our model. So we're going to have an if statement in here. So there's this this DB. I should probably talk about this. So DB, this is short for database. So this is the data that's being passed into the node. It's coming along these input pegs is where that is going. And if we add, actually, I'm going to have to do that here. So we need to be able to specify a file, right? We want to specify what model we're going to load, and that's going to have a path. So we're going to add a new attribute to this script node here. We're going to call it file name, and it's going to have a type string. Chew. And then this is the location of the model that I'm going to want to use. And I've placed it in the same directory as the Pytorch node. So this is vision encoder 500. Now, in the node here, this database, we use this to pass data between nodes. We can also use this to maintain internal state. So the database has this thing called an internal state. And inside of the internal state, you can have attributes. And now this attribute that I specified, file name, that I specified in the UI, this is accessible from the internal state as an attribute name, right, with this dot. But we want to be able to put in something like a Pytorch model. We want to be able to hold a Pytorch model in memory on the script node every single time it gets called and not want to have to reload it every single time. So in order to do that, we're going to have to insert this model into the internal state of the database. So at some point in time, we're going to have a call that looks like we're going to access the dictionary, the attribute dictionary of the actual database. And we're going to insert, we're going to call it the encoder, right? And once we've loaded the file, I'm going to call the object that we produce with Pytorch, we're going to call it coder. So at some point in time, I'm going to define what this is, and I'm going to insert it into the database. We want to check to make sure that this exists first, because we only want to do this once. Once we make the model and insert it, we don't want to have to do it again. So we want to check to see if encoder already exists. So our opening here in the setup, we should actually, sorry, this is in the wrong directory. Oops, not the wrong directory, the wrong scope. So we want to check to see if encoder exists. So if encoder is not if it's not in state dict, do this, right? So now our encoder isn't in the state dictionary. Now in this specific vision encoder is this is the actual model itself. This is a variational autoencoder. So all we do here is I'm specifying the number of channels that I have in my images, the rows and height of the image, and the number of encoding dimensions I want. Please excuse me. The number of encoding dimensions that I want inside of the actual latent space, right? So we define our convolutional models, our layers. So each of these is going to take our image, and then we're going to have a set of convolutions with dilation to create a feature space that we're then going to flatten and sample to get our result, and then we're going to decode out of that feature space back into the image. So these are coding down to the latent space. Then we do a quick run without the gradient to figure out what all the dimensions have to be. And then we do another reverse pass using Pytorch has been kind enough to code convolution 2D and convolution transpose 2D to be inverses of each other. So if you take these arguments in convolution 2D, you can rearrange them appropriately to do the inverse of that operation. So it's easier to make these coders. And then there's an encoding and a decoding call that just passes the data through the convolutional layers and the deconvolutional layers. And then the forward call just samples the results of encoding and then passes the result to the decoder. And then you get the output prediction, and you get the mean and the log variance of the latent space. So we want to be able to load this. Now, the first time we did this, I just put this class definition entirely inside of this if statement, and you can do that. That'll work, but it's messy. So we want to do a local import, which means we have to change the current system path. We have to append the Python system directory that it's using to import modules. So we're going to import sys. And then we're going to get the path, and we're going to append the current path to where we're located. So we're going to get sys path append, and this is in D, live coding, and that should be it, right? So we're looking for module in this path. So now we're going to import model. So I have a model.py here, right? So Python is going to look for a file called model, and then I'm going to say from that file, from model, import dummy bay, dummy bay, no, dummy VAE, variational autoencoder. And that is it. So now we've imported our module here, our model file here. So now we can declare our device. So we need to tell Pytorch what device we're going to be using. So this is device, this is torch.device, and then we're going to use the only GPU I have in this machine, which is CUDA 0. So if you had multiple GPUs, there'd be a unique identifier here that specifies which GPU you're using. And then it's good habit to include an if statement to check to make sure if this is actually available, right? So if torch.cuda.is available else. So this shouldn't cause us a touch. Get ready for a lot of that. This is this shouldn't be an issue for us. I know that this works. If it looks like I'm pulling this out of nowhere, it's because I have it on another screen and I'm just copying what I've already done and I'm walking you through it. So we have the device here, and now we want to we have to specify the actual model and file names and all that stuff. So we're gonna, from the dictionary, we have this database. We're gonna pull our file name that we want to load. So name is db.input.filename, and remember that this file name was what we specified in the UI. And then we're going to make some variables to make things a little bit cleaner. So our coding dims, this is 512 because this is the output I specified in the file that I pre-trained, so I know that ahead of time. And then we need a dummy variable as a placeholder for ahead of time as well. So this is going to be none. And we want to, now we're going to create coder, right? So down here we have coder. Coder is dummy VAE, and we specify our input dimension. So we're going to be operating on an RGB image that's 100 by 100. And then we want to output our code dims. So this is going to be code dims. So we're going to output a list of 512 numbers. And then we're going to put coder on the device, to device. So now this Pytorch model is on the GPU, and we want to save this reference, this coder Python object. We want to save this for later because we're going to call it in compute so we can get our data through the Omnigraph node. So that's what this is for. We add the encoder to the internal state dictionary. And for good measure, we're going to add the device as well. This is the This is like the dark magics, the deep lore. If you are writing a piece of software using Isaacson and Omnigraph, and you find yourself having to do things like this often, where you're going to these private attribute type variables in classes, that's a strong indicator that there's probably a feature need or something, and we are aware of this and we are working on it. But for now, this is what we're doing. Internal state dict, and then our So the idea here is this image buffer. We're gonna get an image. We're gonna rip it from the viewport, and then we're going to put it in the internal state so we can access it with our model, because we're going to be getting that image from some callback function that's going to be occurring possibly asynchronously, and we only want to put data into the model when that callback finishes. We're only going to be doing it one at a time, so it shouldn't cause us any issues. Now, so this is our setup for our internal state. To get our viewport, we want to get our capture from the viewport. So the first thing we need our viewport API. So in our setup, we're going to get our viewport API, and that means that we're going to need OmniKit viewport utility in order to do that. So we're going to import NumPy as NP because I'm not a monster. Import omni.kit.view utility as viewport utils, right? So this is a little helper class that sits in here that we're going to use to get the API that we need to manipulate to get the data we want. So we're going to get our viewport API, and this is the viewport utils get active. This is major hack number one. This get active viewport. That means that if we don't set this to the camera that we want to capture, we're not going to get the image that we want. It also means that if this viewport isn't visible, so if we had this covered up and we tried running this live, we might not also get data because the viewport might not be active, depending on how that's defined. I've had situations where that does cause problems, and situations where it doesn't. I haven't gotten a consistent, reproducible result. So I hesitate to say that that's a thing that always happens, but be aware that that's what we're doing here, is that we're using the currently active viewport to get our data. So now we have our viewport. We want to capture the image. Now, when we capture an image, we're going to be using something called there's a viewport API dot schedule capture, right? So this is going to, and I'm at this point, I am definitely speaking with limited knowledge. I don't have the kind of deep understanding of how this was designed to say with certainty that this is what's happening. But my understanding is that this is spinning up an asynchronous process that is then going to use some other class, which in this case is called the byte capture. So there's a byte capture object that we're going to call to specify how we want the data from the viewport to be captured. So in this case, we want to capture it with just bytes. And then within this byte capture object, we're going to specify a function on capture completed. That's going to get called when byte capture is finished being composed, when the scheduled capture function gets executed. Yeah, it's a lot. So the next thing we have to do is define that function, right? So we're going to make our callback. So this is a function that's not actually a part of the script node, right? This is not one of the 3 functions that are predefined. So you can, I mean, this is just a Python script, right? You can do whatever you want in here. It's extremely dangerous. On capture completed, we're going to need, now there's some malice of foresight here. We need access to our database within capture completed, because we want to push the data into our database within this callback, and that's happening asynchronously. So we're going to use something called partial, which is more Python like dark magics. So there's this thing in Python called functools that basically lets you break the rules however you see fit. And from here, we're going to get partial, which is going to allow us to call a function with an additional input that isn't in its original signature, which is what this DB portion is. So then we're going to need the buffer. So this is part of the signature for this on capture completed. So this byte capture expects this function to have a specific signature. And so that signature is buffer size, width, height, format. And again, I didn't find this thing that we're going through. I didn't find like any. I had a lot of help finding this stuff. So, okay. Now, this buffer is a byte buffer. So if we actually, this might be a good exercise. Let's just print type buffer. Let's do something unscripted. I'm sure nothing will go wrong. So then we'll go down to capture viewport API. So we have to change this. So we want to save our capture. Byte capture, and then this is going to be okay. And we need to import byte capture. That's right, because we don't know what that is yet. All right. And I'm missing a parenthesis. 1, 2, 3, 1, 2. That's, yeah. Okay, so this partial statement, this is something I learned literally yesterday. So what this allows us to do is it allows us to call this function with this as an argument tacked on in the beginning. So you can think of this as kind of like modifying the argument of this onCapture completed function. And we're using this one because we know what its signature is. So we know we're going to get at least these variables, right? So actually we should just do, let's just do this. And then AOV name, I think this stands for Arbitrary Object Variable name, but I'm not sure. But the point is that there are different kinds of captures that are being produced by the viewport. One is called the Low Dynamic Range Color, or LDR color. I think that stands for Low Dynamic Range Color. I hope I'm right, otherwise I'm going to look super dumb. The next thing we want to do now is we want to run the compute. The best documentation links to share for these topics. Well, so that's a great question. We didn't find these through the documentation. The way that we found these was through Kit. So when you go to your OmniKit launcher, right, you can download all sorts of different apps. And so what we did is we went into Kit. And when you go into Kit and you get this option to launch it, you can go into settings, and then here you can open up these actual directories, right? And so now it's possible to just open up one of these directories in VS Code. which is what this is. And so we can go into VS Code and we can actually search for viewport API. And this will show me all the instances within that downloaded folder where this specific instance is coming from. And you can change like what directory you're searching in. You can just right click and then find in folder is basically what we're calling here. Find in folder. Well, come on, where is it? Find in folder here, right? So this just says, okay, look for viewport API in the physics extension. And so a lot of the way that we develop these kinds of programs is because it's like you're building the road while you're driving on it, you know? So some of the stuff that I'm showing you here isn't necessarily written in the docs, but it is in the source code. And it took me a long time to fully appreciate the tools available within VS Code to serve as a search engine for code. But that's how we found a lot of this. And we had the advantage of being able to execute this kind of search on our entire source repository. We need a better way for other people to get access to that kind of information without giving them direct access to our source code, which is an ongoing conversation that's happening within the company. I'm certain of it. Actually, I should probably take a quick pause. Are there any other questions available? Brilliant, thanks. AOV, arbitrary output variable. Aha, thank you, perfect, yes. Yeah, so what's going on here is these, so this viewport, right, this is all running in C++. We're trying to access it in Python, right? So there is this thing called a Python binding, which is a bit of C++ code that takes the data in C++ and wraps it up in these nice little packages called capsules that is used as the generic data type for byte data that's being passed through Python. So all of these I got distracted briefly. All of these buffers and stuff, these are all in capsules, right? And so we need to convert those back. I need to open up my other, here we are. All right, so we want to go down into compute. And so now we're going to just run our test, right? So in our database, we're going to do this capture process again. So we're going to get our current active viewport. And then with that viewport, we're going to get our capture. So this is going to set up that asynchronous call, which is going to lead up to here. So then this should call, and we should see a bunch of print statements on the screen that'll tell us that it's working. So then cleanup, we can keep this pass. All right, now for the moment of truth. The moment of truth. No whammies. I did the wrong thing already. I forgot to change there's a gotcha moment here that we can learn from together. Go back to visual scripting action graph. Script node. You got to click this button here. So when I ran it, it just ran the default script and it threw a bunch of crap in the scene that it didn't want it to go through and manually delete. So we're just going to reset this up quick. So this goes there, and then this, we click on that, and then we type in file name, and we go to string, click on that, and we click OK. Oh, script path. That's down in live coding. Click on the OK button. Don't double click. Guess how many times I've done this. Okay. Perfect. All right, so we can see the data being output from our callback. That's what all this stuff is. So we see we're getting our format is a texture format RGB A8 unorm. I think this is specifying the specific type and ordering of the channels in the camera. So it's red, green, blue, alpha in that order from 0 to 3. And then we can see that the buffer is this capsule object again. And it's empty right now at this address, right? So we're going to want to try and convert that back into an image. And then this is the width and height of the render that's returned by the viewport. So these two numbers should change theoretically if I change the dimensions here. So 1028 by 720, it's going to be exactly the same. Watch, it's a resolution. Yeah, it's a resolution. It's not a size. Of course it is. So anyway, that's the output of our on capture completed. So now for the dark arts. Renato just pinged me with some good information. It's null because it's a void star pointer in C++. So that's the null portion there. So the buffer is in this weird type. So if you go and you Google about this type a bunch, you learn about this thing called a PyCapsule. And there's this method called PyCapsule getPointer that is native to the C-types library. So we want to do C-types, right? Pointer. And the way that this function works, it's kind of different than other functions. I think it's because it's a binding and not a traditional, like, I'm talking off the top of my head again. But you have to specify two different attributes. There's the res type, and then there's the arg type. So the first thing we're going to do is we're going to set these two values, and then we're going to call this function in order to convert our buffer. And the way that the signature looks for this is like the following: C types, Python API, Py get pointer res type. So this is we're telling the function how big is each chunk of data and how much data is there, right? So this is C types pointer, and we're saying we have a pointer of type of size C types dot C byte, because it's a byte array, times buffer size, right? C types, C types. There we go. Next, we have to specify the other one, the arg type. So that's C types Python API PyCapsule get pointer arg type. And this, we're specifying names and types for the argument of the function, but I don't fully understand why this is what it is, but we found this, and I'm going to show you where we found this after I type it in. PyObject C types C char P. And now we can successfully call our we can cast the buffer back into its content. So we can do content equals C types arg types plural. Thank you, Renato. C type Python API pointer buffer none. So this will cast our buffer from, I think this is none because we're dealing with null type. I'm not sure. Again, I don't know for sure. This is a black magic to me. To get our content, and then from our content we get our image buffer. Oh, no name. Yeah. That there isn't a name for that argument. Image content is content.content. And now we can use PIL. So there's the Python image library. From PIL import image. So we're going to use PIL to turn our image content into an actual image object, and we're going to save that within our database. So this is db.internal. Oh my God, every time. Internal state image buffer. This is image from bytes, and it's an RGBA, and it's going to have width, it's going to have height, and I think this is a tuple actually. And then we're going to give it the actual image content. Okay. So now, if we wanted to, we can extract. So this is going to get called, it's going to make our image, turn it into an actual image, a PIL image, and then shove it into our database, so we can access it within the compute. So the image that we're going to pull out in compute may not be, actually probably won't be, the image that we captured on the previous line. The image that we pull out of compute is going to be whatever image is currently in the database since the last time that function completed, right? So again, workaround, but we are aware. The first thing we want to do is we want to get the actual image. So we're going to get our image from the internal state image buffer. So we're going to get our image out, and then we're going to resize the image, because presumably we're going to have a model that requires a specific input. So we're going to do some operations on it to just show that we can do a bunch of stuff to the image before we pass it to the model. If we wanted to plan this better as not just a demonstration, we would do all this like under the hood with actually we'd probably do it up here. Anyway, I'm rambling. So we get our images dot. I want it to be 100, 100 because that's what my model expects it to be. And we have to specify the resampling method. Resampling, there we are. There are a lot of different ways that you can resample the image. So we're not just cropping. We're taking the data and we're changing the number of bins we're putting everything in. And so there's a mathematical function that dictates how much data goes in which bin and how you collapse them together. And each of these represent each of these different functions are a different way of doing that. And so we're going to choose this first one just because it's the first one. And then we're going to save the data, and then that's image. So this is a really recent feature from my knowledge. I mean, I didn't use PIL. There was a while where I wasn't using PIL a whole lot. But you can now just turn PIL images into NumPy arrays. You just pass them as an argument. It's incredible. And it just does the casting for you automatically. And then we do, actually, let's take a look at this. Let's take a look at what this looks like, right? So let's matplotlib.pyplot as prot. And then in here, we're going to do prot.show data. So we're going to do im_show data and plot.savefig. And I'm going to put it with everything else. This is in D. It should be backwards. Coding. image.png. All right. Something else to keep in mind here, because nothing's perfect. I didn't do anything with the cleanup node. So the behavior of this node when we run it multiple times isn't necessarily well defined. So to make sure that we clear all of the internal state, we're just going to decheck this. We're going to change this code snippet back to Fibonacci counting. We're going to decheck that. Then we're going to go to the console, clear this. We're going to hit play. Please don't do this to me. No. This should, oh, it's not printing, of course. I didn't have it printing. So we'll change it back now. And so when I do that, when we toggle this, it flips the internal state back. Error. None type has no attribute resize. None type has no attribute resize. What happened here? This isn't getting saved. The none type is coming from our default none type here. So we've saved none type to that. And this isn't getting called appropriately. Capture viewport schedule capture, yes. Partially PIL code, okay, that's fine. Yeah. Easy fix. But I'm not sure that this is the... So the suggestion was to check if the image buffer is not none before we use it. And we can do this. We can say if image is not none, then do this, and then do that, and then do this, and then do that. But I'm worried that it's going to... Print, no. There we go. All right. And we clear that, and we do that, and we do that, and then 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 we do that. I need to get rid of my additional print statements up here. Too many printing, too much printing, not enough success. If you're in VS Code, there's also a faster way to do that. You can just highlight this and then hit Control / to automatically comment, and then Control / again to uncomment, but old habits die hard. Let's try running this again. Clear that. Clear the memory. That isn't right. That shouldn't be printing. This shouldn't be printing at all. Why is this printing? So this shows to me that this, oh, God, I'm so dumb. I didn't save it. Derp. So this should be printing its none every time, but it's not. Oh, it's because it's working. That's why. That's why it's not printing anything. It's actually working. I'm just assuming that it didn't work. And that's why it's slow, because it's saving an image every time. Stop! Please stop. And I don't like that button. Okay, yeah, here we go, right? So there. So that's the image capture from the viewport. You can see it's squashed horizontally because it's a wide screen capture, and we're not doing anything fancy. Again, we're just squeezing it down. There's some aliasing that occurs when you do this, so it's not like best practice, I'm sure, but for the sake of demonstrating what I want to demonstrate, it's fine. Okay, so we can get rid of this. We can get rid of that. And then finally, we can actually run the model. So if the model is not none, we can do, we want to convert the data into a form that we can actually feed to the model. So we need to permute and trim all of it. So this is torch.permute, because we're going to be rearranging the dimensions. And this is going to be 2, 0, 1, because Torch expects channels first, right? And then the thing we're going to permute, this is torch dot from numpy, and we're going to just convert our numpy data into a tensor. So we're just going to pass it data. And now this gives us our tensor, but now we have to convert it to float, right? Because we're going to be passing it to a neural network model, and I haven't done anything fancy with the typing, so it's going to be of type float. And we only want the first 3 channels, and we don't care about the rest of the dimensions. And because we don't want the model to explode, and I didn't actually record the mean and standard deviation of my training set, we're going to do a quick standardization by just dividing by 255, because the image is an RGB 8, so it's integers, so it goes from 0 to 255 for each channel. So I'm just putting it onto 0 to 1. And now we can pass this to our model. So we want, we actually don't want that. We want mu log var, because we usually don't care about the decoded image. Remember, the first output of the model is the decoded image. We want the result of the sampling, or the thing that we need to do for sampling. We're going to call our, oh, we haven't loaded the model yet. We have to actually load the model. Well, no, we did. That's right. We have to get it from the, we have to get it from here, from the database. So we need the model is equal to db.internal state.encoder, and then device is db.internal state.device. And so we can call now model, and then we're gonna, we don't have to do that. We can just do data.unsqueeze 0. So models operate in batch mode. So the current dimensions of the data is 3, 100, 100. But the model expects batches of images because it's going to be it wants to process a bunch of them at once. So we have to unsqueeze 0 to add an extra dimension at the front. And so we're saying you have a batch of 1. Do it with just a batch of 1. And then we're going to put it on the device, to device. And then we can print let's just print mu. Yeah, and then let's try and save this. And we'll clear that, and we'll clear that, and then we'll do that, and then we'll do that, and then this, and that, and this, and that, and thinking. Hey, look at that. So these are our means. These are our 512 means that our vision encoder is returning to us for the image that we gave it. And I wouldn't use this data for training because we did really like just slapdash standardization stuff, but there you go. And yes, we are losing the alpha channel. We're at 12 o'clock. I think that's the end of the stream technically. But if you wanted to send this out, what you would do here is you would create a add output, and you want it to be of type float list, right? Array. Out data. And we're going to call it out data. We're going to hit OK. And now in our model, in our node, we can just say db.output dot oh, I did not try this beforehand, so if this doesn't work, I'm gonna look super dumb again, but such is the bleeding edge. We stop that, we run this. Oh, that didn't look good. Ugh. Oh, right, yeah, okay. Yeah. All right, I gotcha. That's fine. I get it. I'm complaining. It's complaining because this is still on the GPU, right? So we want to bring this back from the device to the host. So we're going to do mu.detach.cpu.numpy. That button. There we go. So now if I go into Action Graph, and I wonder if I can just do output data to string, and then from string to print. Text, and then that's going to go here, and then we're going to go in there, and we're going to stop printing this, and we're going to go console clear. Why did it print successfully that time? Well, anyway, it's working. So the OGN print text, so we can see that we're passing the data out of the module, out of the Pytorch node, and into another Pytorch node for printing. So this is no longer being printed from this Python script. This is being printed from within the Omnigraph that we produced. And that's kind of all I had prepared for today. I hope that was helpful, and if people like this, I'll do more. I would love to do a stream on like how to build a transformer from scratch. I'd love to do a stream on like the very basics of thinking about building these kinds of simulations in 3D and the unique challenges that arise when you're not just working on something with a pencil and paper, you know, like using quaternions. What's up with that? I think would be a great stream at some point in time. Yeah, so that's all I have. So I'm gonna do the weird, awkward outro thing. I don't know what to do, so I'm just gonna say goodbye and click on the end broadcast button. Okay, see ya. Oh, okay, bye.